Module 2, Lesson 1, Systems of Linear Equation. On this module, we will tackle the systems of linear equation and the different techniques involved in evaluating your system of linear equation, which are direct methods, starting with the decomposition, and iterative techniques in evaluating this system of linear equation. The standard form of your linear equation is given off to be like this, whereby the number of unknown variables is equivalent to the number of equations given off by your given system. If the number of equations is not equivalent to your unknown variable, then you end up with what you call a trivial equation, whereby you end up with several possible values of your unknown variables that will satisfy your given linear equation. As such, if the number of equations is equivalent to the number of unknown variables, then your particular system gives off a unique solution for your x1, x2, and x3 unknown variable. In matrix form, your given system of linear equation appears to be like matrix A multiplied to your given matrix C, which is equivalent to your constant matrix. Your matrix A is denoted to be a 3 by 3 matrix, while your respective matrix X is given off by a 3 by 1 matrix, as well as your matrix constant C. There are several techniques in evaluating your system of linear equations. Among them are your direct methods that were previously discussed on your different math. The first one is referred to as the conventional methods, which are your elimination and your substitution techniques that were taught during your algebra days. And then you were taught different ways to evaluate your system of linear equation using determinants. You evaluate the determinant value and then use Cramer's rule to establish the values of your unknown variables. Determinant techniques like expansion by minor cofactor methods, expansion by row, expansion by column, pivotal element method, and alteration by zero are such determinant techniques, and then later on apply to your Cramer's rule in order to establish the values of your unknown variables. You may also apply inverse matrix, since your system of linear equation can be written off as a matrix. Therefore, in order to establish the unknown variables and evaluate its values, you simply apply inverse matrix of your given matrix A and multiply that with your constant matrix. Thus, several techniques in evaluating your inverse matrices were also introduced during your previous math, like the inverse matrix formula, which is equivalent to 1 all over the determinant value multiplied by the adjoint A transpose, or the row by row transformation that evaluates your inverse matrix by augmenting your given matrix A with a unity matrix. Other techniques like the Gaussian hybrid techniques are also considered to be direct methods, since they directly manipulate your given matrix and evaluate for your unknown variables. Such techniques are referred to as the Gauss-Jordan elimination and the Gauss-Jordan reduction techniques, which were hybrids of your Gaussian elimination technique. In evaluating system of linear equation using this process, you need to follow certain steps and strictly adhere to them, much like your Gaussian elimination technique. And finally, you may also use matrix decomposition, which is among the direct methods considered to be the simplest technique in evaluating any size of your given system of linear equation. This is considered to be the simplest technique because the only prior knowledge you require is simply matrix multiplication, which means that if you know matrix multiplication, you'd be able to evaluate matrix decomposition and solve for the unknown variables. Iterative methods are also used in evaluating your system of linear equations. As such, you have the Gauss-Jacobi method, the Gauss-Seidel method, and the relaxation method. There are several ways to do matrix decomposition, one of which is called the Krauts or Cholesky's method. Under this direct method technique, you often decompose your matrix A into its respective factors L and U. Hence, some textbooks refer to this technique as LU decomposition, whereby your matrix L comprises the following elements: L11, L21, L31, L22, L32, and L33, while the rest are zero, and your U matrix comprises of U12, U13, U23, a main diagonal made of one elements, and the rest are simply zero. The Krauss-Cholesky's method decomposes your matrix using a simple matrix multiplication and derive its formula from the factors L and U. Thus, for step 1, we simply evaluate L11, which is then in turn simply equivalent to your element A11 of your given matrix. Your L21 is simply equal to A21, your L31 is simply equal to A31. The next step involves in solving this sign, U12 and U13 of your U matrix. Your U12 is simply equivalent to the element A12 of your given matrix divided by the previously solved L11. Likewise, U13 is simply equivalent to the element A13 of your given matrix divided by L11. And then step 3 involves in solving for L22 and L32. Based on the formula, using matrix multiplication, your L22 element is simply equivalent to the element A22 subtracted with your element L21 multiplied with your element U12, while element L32 is simply your given matrix element A32 minus element L31 multiplied with U12. For step 4, we simply evaluate for element U23, which is equivalent to the formula, the given matrix element A23 minus L21 multiplied with U13 divided by L22. And finally, the last step involves solving for your element L33. Element L33 is simply equivalent to your matrix element A33 minus L31 U13 minus the product of L32 U23. The other method in decomposing your matrix is referred to as the Doolittle method. A Doolittle method, much like your Krauss or Cholesky's method, decomposes your matrix L into its factors L and U, whereby your matrix L comprises of these elements L21, L31, L32, with a main diagonal full of ones and the rest zeros, and your U matrix to contain the element U11, U12, U13, U22, U23, U23, and the rest are zeros. In decomposing now your given matrix A into a Doolittle method, step 1 this time involves solving first U11, U12, and U13, much like your Krauss or Cholesky's method. This time, U11 is simply equivalent to A11, U12 equal to A12, and your U13 is simply equivalent to A13. The next step, step 2, involves solving L21 and L31, whereby you divide your given matrix element A21 with U11 to solve for L21, and to solve for L31, you divide your given matrix element A31 with U11. Your step 3 involves solving for U22 and U23. U22 is then evaluated as your given matrix element A22 minus the product of L21, U12, whereas U23 is simply equivalent to your given matrix element A32 minus the product of L31, U12. Your step 4 involves solving this time L23, which is equivalent to your given matrix element A23 minus the product of L21, U13, and divide their difference with U22. And finally, your step 5 involves solving U33, whereby it is evaluated from your given matrix element A33 minus the product of L31, U13 minus the product of L32, U23. From there, after factoring your matrix A into its given factors L and U, after decomposition, your matrix equation now becomes like this, whereby you have L, matrix L multiplied by matrix U multiplied by your unknown variable matrix X is equivalent to your matrix C. We then assume that your matrix R, or any of your given matrix, for example, in this case R, is equivalent to the product of U matrix U times U matrix X. Therefore, our equation is then reduced to matrix L multiplied by matrix R, which is equivalent to matrix C, serving as our equation 2. And from which you would see that when solving for matrix R, we apply forward substitution, reverting your given matrix form of equation into your given standard form of equation, and solving for the first variable, substituting it on the succeeding equations until you solve all the other variables. After solving them for matrix R, we then revert back to our first assumption, whereby matrix U is multiplied to your matrix X, equated to your matrix R, and solve for the unknown variable matrix X by using this time backward or reverse substitution, starting from the last equation and reverting your given matrix form into a standard linear equation form. Solving for the last variable and substituting them to previous equations, thus reverse or backward substitution is applied. So basically, when summarized from your given matrix equation, you evaluate your matrix variables of matrix R and then solve for the unknown variable matrix X using your initial assumption of equation 1. Let's try it out on this given particular problem. Determine the unknown variables using Kraut's method, given our system of linear equation to be this. Therefore, we simply write down first your given system of linear equation into a matrix format like this. And then factor out your matrix A comprising of the following elements, which are referred to as the coefficients of your unknown variables, into its factors L and U. Since we're using Kraut's or Cholesky's method, therefore your matrix L will appear to contain the following elements, and your matrix U will then contain the following elements. We begin by solving then these particular elements using your formula for your Kraut's or Cholesky's method. Therefore, our L11 is simply equivalent to 6, our L21 is simply equivalent to -2, our L31 is simply equivalent to -3. Whereas our U12 on the next step involves in dividing A12 with L11, thus giving us a fractional value of -1/3. And for your U13, when evaluated using our formula, it then gives us a fractional value of -1/2. The next step involves solving L22 and L32. Knowing the formula for your L22 and L32, the solution then would appear like this and would have an L22 value of 13/3, with an L32 value this time of -3. Then the next step involves in solving U23. Solving U23 gives us this particular solution and then gives us a value of 9/13, while L23 is then evaluated using this formula, ending up with this solution, giving us a fractional value of 1/15/26. Thus, based from our decomposed matrix, your L matrix would contain the following elements, and your U matrix would then contain the following elements. From your given equation 2, whereby we evaluate matrix R using forward substitution, the matrix equation then would simply appear like this. We then revert this matrix equation and convert it back into a standard form of equation. And looking at the standard form of equation, you will notice that on equation 1, you'd end up with the following given equation: 6R1 plus 0R2 plus 0R3 is equal to -11. Thus, we would end up with an R1 value equal to negative 11 over 6. We then substitute R1 to equation 2, which is given to be negative 2R1 plus 13 over 2R2 plus 0R3 is equal to 12. Upon doing so, we could now solve for R2 since we already know R1, giving us an R2 value of 25 over 13. We then substitute our R1 and R2 in equation 3, which is equivalent to 3R1 minus 3R2 is plus 115 over 26R3 equal to 13. Your R3 then would simply be equivalent to this solution, giving us a value of 3. Thus ending up with matrix R to contain the following values: for R1, negative 11 over 6, for R2, 25 over 13, and for R3, 3. We then use this value on your previous assumption, which is noted to be equation 1, whereby matrix R is equivalent to the product of matrix U multiplied to your matrix X, which then appears like this given matrix equation. Looking at this matrix equation, we simply revert this into your standard equation form and then start from equation 3 and solve for the last variable, hence referred to as reverse substitution or backward substitution. And upon doing so, we end up with an equation 3 equal to 0x1 plus 0x2 plus 1x3 is equal to 3. Therefore, our x3 is simply equal to 3. We then substitute x3 to your previous equation 2, which is written to be 0x1 plus 1x2 minus 9 over 13 x3, which is equivalent to 25 over 13. When substituting then your variable x3, your x2 is computed to be this solution with a value of 4. We then substitute x2 and x3 on your previous equation 1, given by the form 1x1 minus 1/3 x2 minus 1/2 x3 is equal to negative 11 over 6 on your given matrix equation. Substituting x2 and x3 gives us now a value of x1 equal to 1. This ends the module.